representing 4 stages. There's stage 1, 2, 3, and 4. 4 stages. Okay, the same convention, same symbols that we use apply here as well. So let's look at this. What's coming in is your liquid stream, X naught, so that we can write that as L naught. Its concentration is X naught, its total flow rate is L naught. Okay, so what's coming out at the bottom, its concentration will be Xn, and its flow rate will be Ln. On the vapor side, you've got Yn plus 1, so it'll be Vn plus 1. We're saying N, but remember, because it's the 4th stage, this will be L4 and this will be V5. Okay. On the top here, you'll get Y1, which is the concentration, and you've got V1, which is the flow rate. So leaving a stage, let's look at stage 1. What is leaving stage 1? You've got Y1 and you've got X1. They are in equilibrium with each other. So when I want to find the relationship between these two, I have to use equilibrium data. Okay. On the same side of a stage, directly next to each other, you've got X1 and Y2. How do I find the relationship between these two? That will be from the operating line. If I go to stage 2, same story. What's leaving stage 2? You've got V2 and X2. Okay, leaving stage 2 is V2 and X2. What's on the same side? So you talk about stage 2. X1 and Y2 are on the same side of the stage, so they'll be related by the operating line. Similarly, Y3, X2 will be on the same side of the stage, and their relationship will be given by the operating line. The relationship between Y2 and X2 is given by the equilibrium line. Okay, there's a question. Is M the same for the entire tower? Yes. What is M? M is the total throughput for the system. Total throughput will not change. So if I've got, for example, in stage 1, I've got liquid that's coming into stage 1 that is, let's say, 20 moles per hour coming into stage 1. Okay. As it is leaving stage 1, its flow rate may change because some of the solute is moving. Okay, from the gaseous phase to the liquid phase, or the other way around, doesn't matter. Some of the solute is moving. So it's coming in with 20, it is going out with 21 moles per hour. But when I add the V phase and the L phase, it must give me the same value. So if I had originally 20 coming in on the top, and I've got 30 coming in at the bottom for the V phase, 20 moles per hour for the L phase, 30 moles per hour for the V phase. The sum of the two is equal to 50. 50 moles per hour is the total throughput through the system. That is the M. So that M will be maintained throughout the entire tower. Okay, the M will be maintained throughout the entire tower. As it is losing moles in one phase, it will be gaining the equal amount of moles in the other phase, such that M is the same throughout the tower. I hope that answers your question. People, any other questions here? Okay, so the solvent stream V contains components A and B with no C, and the solvent stream L contains A and C with no B. Okay, so it is saying that majority of the streams, that's what it's talking about, right? A, remember, is your solute. So majority of stream V will have component B, and it will have some solute A. Majority of the L stream will have component C and some of the solute A. But they won't mix with each other. So you won't get, for example, component C in the V stream or component B in the L stream. The two streams, L and V, are immiscible in each other with only A being transferred. Let's put this into a diagram. If I plot Y versus X, I plot this, Y versus X. Then we know from Henry's law, we can get the equilibrium line. There's the equilibrium line. That's from Henry's law. Okay, that relates Y and X. So it will relate equal subscripts, right? So the streams that are leaving the same stage. The other one is the operating line. Where do we get the operating line? It is this equation here that we've got. I have to plot this equation. Okay, this is relating yn plus 1 to xn. I plot this equation. Now this is the operating line. So there's my operating line there. If I want to work out how many stages do I require in order to get a certain concentration. So I'm starting off with a certain concentration x0, but at the end of my multiple stages, I want concentration xn. Okay. How many stages do I need? How many equilibrium stages do I need to get to xn? We use what we call a McCabe-Thiele diagram. McCabe-Thiele diagram is a stepping off between your equilibrium line and your operating line in order to get the number of stages. I'm only introducing this here. We deal with it much more later on. Okay, but I want you to understand the concept, because when we talk about operating lines and equilibrium lines in the next section, you'll know what we're talking about. You know where we're leading to. Okay, so if I step off stage 1, stage 2, stage 3, and stage 4. Stage 4 gives me xn, which tells me that I actually need 4 equilibrium stages if I want to get from x0 to xn. Let me erase that and talk about some other stuff on this diagram. If I look at any point on the equilibrium line, it must give me the same okay, that's not me driving around. Okay, can you hear someone straight? If I consider any point on the equilibrium line, let's consider this point here. This is on the equilibrium line. That must give me the relationship between the concentrations leaving that particular stage. So you can see here I've got x3 and y3. It has the same subscripts. Same subscripts because they're in equilibrium with each other. Okay, similarly, consider this point. You can see the subscripts y2 and x2. Okay, so it's got the same subscripts because they're in equilibrium with each other. If I look at the operating line is different. So if I consider a point on the operating line, there, then I get y4 and x3. If I go to my diagram, y4 and x3 are next to each other. They're on the same side of the stage. Okay, so that is how we got the operating line. You can consider any point, y3 and x2, etc. People, questions here? That ends the section on equilibrium studies. It is now 9:24. I want to introduce absorption. Okay, we won't go into it in great detail, but I want to introduce it, and then and obviously continue with it next week. But this one is complete. Okay, let me stop sharing here and start sharing the next one. Okay. Okay, so we finished the first section, which is equilibrium studies. There's a TUT that's available on Moodle, TUT 1, very simple, straightforward TUT. Please go through that. We will discuss that TUT next week, Tuesday, and you'll write your first tutorial assessment on Tuesday. Okay, it will be online. Remember, the tutorial tests can cover anything from your tutorials as well as the section that we covered on equilibrium studies. So I can ask you anything on that section. Okay, so all the tutorial test is doing is making sure that you're keeping at the same pace with everyone else as the class is moving forward. So I can test you on anything that has been covered in that section. Okay, so make sure that you go through the work, that you understand it. If there's problems, contact me. We'll make sure that you understand it. Okay, and you'll write your first assessment. Let's go on to the next section. The next section talks about absorption. Absorption, right? Remember, we spoke about 3 major sections. Okay, the first section, absorption, second section, distillation, third section is liquid extraction. It's going to cover some repetition here. And I'm going to go through it fairly quickly because we've just covered it under equilibrium studies. Okay, remember we said that now we'll only talk about gas liquid, because in equilibrium studies we were talking about any system. Now we're talking specifically gas liquid system. Okay, gas liquid system. So you've got a gas, you've got a component in the gas stream that you want to remove, that you want to recover. Okay, that is your solute, and that solute is absorbed into the liquid phase. Okay, so it's the same slide that we had previously. You've got a relationship between the concentration in the gaseous phase and the concentration in the liquid phase. That relationship, the equilibrium relationship, is given by Henry's law. Okay, we've covered that. It goes on to talk about Henry's law in detail, but we've just covered it. Why are these slides repeated? Because previously we spoke about equilibrium studies and distillation, and then started absorption. Okay, so the absorption, I had to recap on what was covered in your previous sections, but we've just covered this. If there's any questions, you're welcome to ask. But very briefly, Henry's law, that's Henry's law. H is Henry's law constant that you can find from tables. We can relate, instead of writing Henry's law as in terms of partial pressures, we can relate it using a mole fraction. Okay, and the Henry's law now becomes H prime, or the constant becomes H prime, and H prime is given by H over P. Same example, we've covered this example already, so let's not go through that in detail. And the equilibrium studies, single stage equilibrium contact. We've done the balances for a single stage equilibrium contact. This we haven't covered. So let's go through this in a little bit of detail. Single stage equilibrium contact specifically for a gas liquid system. So once again, previously we spoke about any system, okay, any two phases. Now we're talking very, very specifically about your gas liquid system. So in the usual case, gas liquid system, the solute A is in the gas phase, which is in the V phase, along with the inert A, inert gas that we've got in the gaseous system, which is called component B. And in the liquid phase, you've got L, along with the inert water phase, which is C. Okay. Assuming that A is essentially insoluble in water phase, and the water does not vaporize into the gas phase. So those two streams, B and C, do not mix with each other. You'll have a B in the vapor phase, and you'll have component C in the L phase. Okay, you won't get it in the other phases. So if that is the case, the gas phase is a binary system, binary meaning two components, binary system of A and B, and the liquid phase is a binary system of A and C. Okay. Since component A is the only component that redistributes between the two phases, a balance on A can be written as follows. Now I'm going to leave this for you to derive. You're going to derive this equation. We did a balance. What diagram are we talking about here? It's the same diagram that we had before. You've got L0, you've got V2, L1, and V1. It's the same diagram that we had before. But we're rewriting the balance. So our original balance said L0 X A0. Or you can just have it as X0, it doesn't matter. Plus V2 YA2 equal to L1 XA1 plus V1 YA1. That was the original balance that we had. We're rewriting this balance in terms of writing it as inert values. So we define two new terms. One is L prime and the other is V prime. So what is L prime and V prime? L prime is the mole's inert water, component C, and V prime is the mole's inert A, which is component B. Both L prime and V prime are constant and are usually known. Okay, so these are constant values. They will not change. And why are they not changing? Because component B and component C are not moving between two phases. So when we're talking about the inert value, it is only that value that is in that stream. Okay, the inert value in the gaseous stream and the inert value in the liquid stream. So I want you to derive this equation from my original balance equation. Okay, you will see when you derive it that in order to get from one to the other, V prime is essentially equal to V into 1 minus Y. If we make V the subject of the formula, V is equal to V prime over 1 minus Y. The same thing as the X values, L prime equal to L into 1 minus X, and L is equal to L prime over 1 minus X. Okay. So looking at this equation, and we only use this equation when we're talking about absorption. Just take this out. Looking at this equation, if I know what L prime is and V prime is, those are the inert values. Okay, so if I've got, let's consider the CO2 air system, CO2 air water system. CO2 was the solute. Okay, so that is what's redistributing between the liquid phase and the vapor phase. The liquid phase had component B. The vapor phase had component C, or it was the other way around. Okay. The inert values, so the pure water that's flowing in the liquid phase is not changing. So how much of water is coming in at the top will be equal to how much of water is leaving at the bottom. Similarly, the air that's carrying the CO2 coming in at the bottom, that air will be exactly the same value as the air that is leaving the top of the column. It is not changing because the air is not moving into the different phases. It's staying in that vapor phase. Okay, so V prime and L prime are known. If I know the concentrations coming in, so I know how much of CO2 is coming in with the liquid phase, say not, and I know how much of CO2 is coming in with the vapor phase. Then the only unknowns in this equation, it's two unknowns, will be XA1 and YA1. Those are the two only unknowns in this equation. Okay. Now those two unknowns, you can see it's got the same subscript, 1. So I've got one equation here, but two unknowns. I need to find a second equation. And the second equation that we find that relates these two is the equilibrium equation, which is Henry's law. Okay, Henry's law is the equilibrium relationship that relates XA1 to YA1. Now I've got two equations with two unknowns, and I'll be able to solve them simultaneously to get YA1, XA1. Questions here, people? If there's no questions, then this is an example, a class example that we have to do. But what I want to do now is leave this to you to attempt. We will discuss it. We will do it in detail the next time I see you on Friday. So we'll go through it in detail. Okay, but just to see whether you understood what we've been talking about now, I'll leave this to you to attempt. Okay, you can attempt this and we'll discuss it in detail on Friday. People, I will stop there. Are there any questions whatsoever? We only had 21 people attending this class, so 50% attendance, which is not good.
Sorry, sir.
Yes, talk to me.
Do we need to get